Okay, so real quickly, trying to review the notes from Friday for those of you that were not in class. We have what is the indefinite integral. And you'll notice that before we started this section, we mainly worked with definite integrals. And in this video, we'll be adding the indefinite portion to our knowledge. So first of all, what is it? Well, here's the official definition. Let f be any function such that the derivative of capital F equals the little function f of x. Then the integral of little f of x would equal capital F of x plus c. So this has a lot of meaning. First of all, this expression right here, this little equation, what it tells us basically is that capital F is the antiderivative of little f of x. That's what this means. Because if you take the derivative of capital F, you get little f of x. So that implies the relationship is capital F is the antiderivative of little f of x. Okay, so now the part that you definitely need to know how to do is how to evaluate it. And this is going to give you the key. You see evaluating an indefinite integral, and you'll notice first of all that boundaries are gone. With the definite integral we had boundaries, and those boundaries told us where to start and where to stop, and also the definite integral signified net area under a curve. Well, with the indefinite integral we get rid of the boundaries and it no longer means the net area under the curve. What it means is the solution to the differential equation dy dx equals f of x. So it's what we've already been doing, but we are giving it a little bit different notation. So it's important to note, here we go, the solution to an indefinite integral is the family of function whose derivative is f of x, little f of x. So in the past, you were given an example like this. dy dx equals 2x. And you were asked to solve this differential equation, and basically that means find the function whose derivative is 2x. And normally you just took the antiderivative and put plus c to signify that you could have any constant. Well, that is exactly how you evaluate an indefinite integral, because an indefinite integral is asking you the same thing. It's asking you what family of functions would have given you 2x as its derivative. So its answer is simply going to be the antiderivative of 2x, which in this case is x squared, but you always have to have plus c. So you have to understand that this new integral, this indefinite integral, no longer means net area under a curve. It literally means all of the possibilities whose derivatives would be 2x. And I want to show you what that looks like graphically. I have it here on the calculator. And this is it. This is what we're talking about. So the solution is x squared plus c. So you can see I have a lot of different values for c, and it creates that family of functions made of parallel curves that give you represent the potential solutions for that equation. So let me show you a different example. So we have here the indefinite integral of x squared plus cosine x dx. To solve this, or to evaluate this, you simply take the antiderivative of x squared. In this case, it will be x to the third power at 1 multiplied by the reciprocal, so 1/3 x cubed. The antiderivative of cosine is sine, and then plus c. And that's it. It represents the family of functions whose derivative would give you this function here. So that's what an indefinite integral is, and that's how you evaluate it. In the next series of videos, we're going to talk about u substitution. And basically what we're going to do is we're going to complicate this function a lot more. We're going to make it a little bit more difficult to find the antiderivative, and u substitution is going to give us a tool for doing that. But in reality, u substitution could be used not just for indefinite, it can also be used for definite integrals. So this is it for the first part of the lecture.